All right, everybody. Today we're going to learn about how derivatives work and what they do for you. Now, there's other theory videos out there. That's not what this is. This is going to be the down and dirty, what does a derivative do for us when dealing with finding relative minimums and maximums, specifically in polynomials. All right, we're going to use this to help us sketch or help us graph. So the one thing that you do have to know how to do is find a derivative. And I'm going to give you, once again, not the theory behind derivatives. If you want that, watch a different video. For this, we're going to go with specifically how do I calculate a derivative. First, you should note how we actually write a derivative. A regular function is written like a of x. A derivative is written a prime of x. So this is the notation for a derivative. All right, so with that in mind, let's go ahead and figure out how we do a derivative. To do a derivative, all we do is we need every variable, like the x, we need it to have an exponent above. Now, if it's already written, we don't need to write it again. If it's not written, we're simply going to add them in. So I'm going to go down all of these examples that I have, and well, that's the only one I needed to add. The second piece we're going to do is we're going to take the exponents for every x, and we're going to bring it into the front and multiply it by whatever the coefficient is. And on the screen that I have in front of me, I have two examples here, and then we'll scroll down and do the other two. Now, if there's a 1 as a coefficient, you simply multiply. In my case, I'm multiplying 2 times the 1, and I'm going to get 2x. And then I go to the next piece. I'm going to take the 1 times the 3 and get 3. And every time, this is important as well, every time we do a derivative, every time we move it, we remove 1 from that exponent. So down here, I really get the first, and I really get x to the 0. But we don't write x to the first, we just leave it as x. And we almost never write x to the 0, we just don't write it. And the 1 at the end, we don't even deal with that at all. So, because it doesn't have an x, so we just don't deal with it. Let's go to the next one. We're going to bring down the 3 multiplied by negative 2, we get negative 6x. And we subtract 1, and we get a 2. I know I have multiple colors here, but you can handle that. I'm going to take the 1 times the 9. I get plus 9. And I remove 1 from the exponent. So I get x to the 0. And we've already talked about how we don't write x to the 0. And finally, it's just a constant, so we don't bother with the constant. For our derivative, we don't worry about that. Now, here's one. I'm not going to do all of the circling and arrows and so on. I'm just going to do it the way your teachers would probably jump in. This one's going to be a 12x to the third plus 6x squared minus 10x. I bet you can follow what we're doing there. And that is the basic idea of a derivative. Now, I have one example here because my goal isn't just to find derivatives. I suppose that's a nice novel activity, but it's not really all that useful to us. I want to use this derivative idea for something, and I want to use it to draw an accurate graph, hopefully without a calculator, but if I need one, I'll grab one. So here's what I'm going to do. The first thing I'm going to do is identify my zeros in a graph. So before I even deal with the derivative, let's move it out of the way. Let's go ahead and deal with the zeros like you normally would. I'll use gray to calculate zeros. 2x to the third plus 2x squared equals 0. I'll factor. Let's see, 2x squared, x plus 1. So I'm going to have a multiplicity of 2 when x equals 0. And I'm going to have x equals negative 1. So I'm going to come over here to my graph. I'm going to graph the x equals 0 and x equals negative 1. There's my x equals 0 and my x equals negative 1 with some really nice, obnoxiously big black dots. All right, let's move this stuff off to the side. If we need it again, we'll be able to look at it. Now let's take a look at our derivative and what in the world it does for us. So we're looking right up here. We're going to get 6x squared plus 2x. In this example, we're going to take a derivative, and then we're going to immediately try to work on finding the zeros of the derivative. Once again, this is not a theory video. This is just how to do it. So I'm going to find the zeros of 6x squared plus 2x equals 0. We just did that in gray in the previous question. So let's do it here. Factor. I'm going to get 3x plus... Oh, drats, I did something wrong. All right, this should have been, you might have caught this mistake. This should have been a 4, right? Just so that we're clear, because when this comes down here, it should have been a 4. So that changes this to a 4. There we go. We're back on track here. So that changes this to a 4, and that changes this to a 2, And we're right back on track. So sorry about that earlier mistake. So now I have 2x equals 0, so x equals 0, and 3x plus 2 equals 0, so x equals negative 2/3. And those are going to be my x values, my relative mins and max. And at this point, the truth is I probably will grab a calculator. For the purposes of a really short video like this one, I'm actually not even going to do the calculation. All I'm going to do is tell you what to do, and then I'm going to sign off. You can try it yourselves, because it's just a matter of using a calculator. At this point, we know that when x equals 0, we're going to have either a minimum or a maximum. So all you need to do is put 0 into your original equation, figure out what f of 0 is, and you will have 1. It'll be 0, and in this one it's going to be 0. You're going to have your relative min or max. There's no way to know whether it's a min or a max without knowing n behaviors, but I'm going to make a little dot there, and maybe we will finish this one out. So there's our first one. Let's get rid of the markings just to keep things clean. And now let's do the same thing. I'm going to take negative 2/3 and I'm going to put it into my original equation. Now for this, I actually am going to grab a calculator. I know I vacillated between using one and not using one. So let's go ahead and use it. Let's get the screen split. And let's take a look at what we're doing here. So I got 2x to the third. So I'm going to go 2 and then negative 2/3. And then I'm going to go to the third power. There we go. And plus 2x squared. So plus 2 and my negative 2/3 and squared. And hit enter and see what we get. So we get, I'm going to estimate this to negative 0.3. I'm going to estimate it to 0.3 because that rounds. And here's what we came up with. So I have a negative 2/3 and 0.3. So I'm going to graph this. Negative 2/3 would be, I don't know, let's see if that's negative 1/3. Here's about negative 2/3. And 0.3 is probably about a third of the way up as well. So I'm going to go ahead and make this mark. Now this isn't perfect, of course, but it's probably pretty darn close. But what I do know is that my graph at its absolute peak or at its absolute bottom will be hitting these two pink dots. Let's declutter the image just a tiny bit. And what I'm going to do is I'm going to couple these pink dots with end behavior. End behavior of something that is cubic is going to be, because of the positive coefficient, is going to be down, up. So now I can go ahead and sketch myself a pretty accurate line. Here's what I know for sure. I'm going to come up through my 0. I'm going to cross through this pink dot, which is the absolute, because of the way I'm curving, it's going to be absolute, a relative max. I'm going to curve down, and now this one is a relative minimum because that's what our derivatives do for us. And this one was also a multiplicity of 2, so we're going to bounce off of that point. We're not going to cross through it, and we're going to come back up. And now, even though I don't really have good data on what these dots are going to look like and what these dots are going to look like, I could always improve that with just some tables of values. I have myself a pretty good looking and a pretty accurate graph of the original polynomial f of x. And those are the basics, very, very basics, of how I use derivatives in action.